Welcome to Spatial Signals. It's a podcast about remote sensing and geospatial science, but more importantly, the people behind it. I'm your co-host, Dr. Brad Shellito, and with me today is your other co-host, coming to us from his pirate radio station out at Old Ephraim's Grave at Logan Canyon, Mr. Chris McGinty. Chris, how is Utah treating you today?
It's a beautiful, wonderful day here in northern Utah, and Old Ephraim is, if you haven't read the story and you want to learn about some, a very famous bear in northern Utah, you got to go, read about this Old Ephraim. It's quite the story, Brad.
So you're just hanging out there, telling stories, pouring one out for Old Ephraim here today?
Yes, you bet. Yeah, I gotta do what I gotta do, and this is a very fitting place for today's podcast. So we'll see how it goes. How's Ohio? I gotta ask.
Oh, Ohio it's spring, so Ohio doesn't get much better than this, right? Ohio in spring is a beautiful place.
I'm sure it is.
Hashtag weather fans, always there for you. Well, for those of you just joining us, this podcast is sponsored by AmericaView, the National Geospatial and Remote Sensing Network that's dedicated to empowering Earth observation. Now, AmericaView has been around since 2003. It has grown from a program just within the state of sunny springtime, Ohio, to a network of programs that stretch across the United States, working with remote sensing, GIS, and geospatial technologies in all forms of outreach, research, and education. But today is a special episode. It is our fourth episode of our sub-series here on Spatial Signals that we call The Squared Circle, in which we have a whole group of guests in to wrestle with a particular topic. And here in round 4 of The Squared Circle, we're going to be grappling with remote sensing and wildfire management. So I'm going to throw things back to Chris for a little background on today's match.
Well, thanks, Brad, and I'm going to apologize because I very well could lose my voice, but that might be for the best. We'll see how that goes today.
All that partying at Old Ephraim there.
Oh man, I'll tell you what. Somebody shared something. It must have it was definitely the bear. We'll blame it on the bear.
Blame the bear.
Yes. Anyway, or maybe it was wildfire smoke. Maybe not yet, but it will be eventually.
Wildfire set by a bear. Yes.
Right there you go. Anyway, so leading into this. Super excited to have this incredible group of people here today to talk about this really important topic, and that is wildfire and remote sensing and Earth observation, and talking about the use of remote sensing, specifically, addressing these wildfire issues, Brad. And wildfire is one of these really incredibly complex natural challenges that we face. It affects communities and ecosystems, air quality, water, you name it, around the globe. And really, remote sensing over the years has become this powerful tool, really to help understand and respond to these fires, but also to help predict them, to understand how we can better rehabilitate lands after the fires, their greater global impact. And we're starting to see with changes in climate and changes in things that are happening, around the globe, these fires are becoming, beasts unto themselves and, creating their own weather patterns. And even to the degree that some of these massive stand replacing fires like they've had in Canada over the last 20 years are so big, so hot, so intense that they actually look, Brad, like a nuclear explosion. And so these are really big topics, and the group of people here that we're going to talk to today have a broad array of expertise in looking at fires and impacts and predictions and sharing data about fires and remotely sensed data at that. So this is a really neat topic. It's a really incredibly fast evolving topic, and so there's always new things that are going on. There's new sensors going up. There's new data that's available. There's new models that are made to help us with all the things we just talked about. But also there's this other component about just education about wildfire and understanding the greater impacts of fires and how we use these technologies and why we use these technologies, Brad. So today is discussion. We're going to look forward to wrestling with these issues, and we're hoping everybody will jump in and really grab these things and show everybody what the importance of remote sensing and wildfire really are and those ties between the two. So I'll kick it back to you, Brad, but super exciting today. This is going to be a great topic.
All right, sounds good. Thanks very much, Chris. Well, for our listeners out there, your full card for round 4 today is 3 very special guests, all of whom have previously been here on the show. You can go back into our archives and hear individual episodes with each of them. But the big thing is all of them have extensive experience with different aspects of analyzing and managing wildfires with remote sensing and geospatial technologies. So first off, without further ado, I'd like to introduce Dr. Sam Batsley from the Space Science and Engineering Center at the University of Wisconsin-Madison. Sam, thanks for coming on today.
Thanks, Brad and Chris. It's a pleasure to be here.
Our second guest is Dr. Nancy French from the College of Forest Resources and Environmental Science at Michigan Tech Research Institute. Thanks so much for coming back today, Nancy.
Oh, it's great to be here and hear you, Brad and Chris. I'm getting ready to participate.
And last but not least is Dr. Aaron Maxwell, who you've heard a little bit from before as our emergency backup co-host, but he comes to us from the Department of Geology and Geography at West Virginia University. Aaron, thanks again for coming on.
Thanks for inviting me, Brad and Chris.
Well, as Chris mentioned, everything today is dealing with wildfires. And our first question here is in our wrestling match is, what role does remote sensing and GIS have in wildfire management in your own work? Just a way of background.
Well, for me, here in Wisconsin, we are working on a variety of things related to fire, and they all are integrally related to remote sensing and GIS. In that, one of aspects is we sort of think of the whole fire cycle. You know, there's like pre-fire, fire, post-fire, and the part of it that we work on is detection, like being able to identify thermal anomaly that could be a fire and being able to look more closely at it. But we use weather satellites to actually see the pixel that is hotter than its surrounding area. And then we use other layers of GIS to figure out if it's something we already know about or something new. And so GIS is a super important part of the detection process for us.
So with that's a good lead-in, Sam, to what I've been working on in my career. Because when I started, there was some work looking at how to use satellites to see where the fires were. But just in the last 25 to 30 years is when we've been able to actually quantify how much fire we have on Earth. We kind of knew where the fires were with reconnaissance aircraft or, people on the ground. But being able to count them all up and know where the fires are, that was something that's matured just in the last 20 years. And for my work, that's important because the primary thing I look at is how the fire impacts what's on the ground, the fuels. I'm an ecologist, so I care about what's out there in the forest or grassland that's burning. And then how does that translate into, when you have a fire, how does that translate into the smoke that comes up? How do we know how much is burned? Remote sensing helps us with that. That's important because the emissions from fires impacts air quality. It impacts the carbon cycle. So the amount of all that material that's going up is changing the way the carbon moves through the Earth system. And so you can think about how remote sensing can be used to count up the space that's happening and then also look at what's happened, what's there that actually burned. We call that the fuels. That's the work I've been doing all these years.
Yeah, I mainly am interested in fuel mapping and kind of at a large spatial or a high spatial resolution. So I got involved with this through collaborations with the U.S. Department of Agriculture, Northern Research Station, and Southern Research Station. A lot of people think more about the West when they think about fire, but we also have fire-prone areas in the East. Our field sites are mainly in New Jersey and the Pine Barrens, and we also have some sites in pine-dominated stands in Florida and Georgia. We're mainly interested in mapping fuels using terrestrial laser scanning, so LiDAR on a tripod, basically. And we're interested in trying to figure out ways to take those plot-level measurements, estimate fuel, and then scale that up to more stand-level estimates.
Well, you guys have mentioned things about examining fuels. You've been looking at detection. It's sort of the whole cycle here. There's stuff there that's going to catch fire. We're going to find it. Eventually, the fire will be burned out, and we'll have to deal with the aftermath of it. But where do you see things with remote sensing here, particularly with risk assessment and preparedness? If the fire is going to be happening, how does your work play in with that?
Well, I can speak to the post-fire issue. One of the risks that we are asked to help manage or provide information for is the potential of post-fire mudslides and debris flows that happen when an area gets destabilized by an intense fire. And if it's in an area of steep terrain and there might be like a reservoir down the valley or maybe a community, there's concern that a large rain event, or not even a very large rain event, a rain event starts to build up and pass over that burn scar area. It can cause debris flow and landslide because the soil has become hydrophobic and it just sloughs off the ash, and the roots are gone, the trees, everything that stabilized that soil is missing. And so it just creates these awful problems and huge risk for the communities downstream. And so what we've been trying to do is shorten the period of time it takes to map the post-fire area, and using satellite remote sensing. And we do a data fusion thing where we combine 4 different sensors that have different periods or different times and different levels of resolution. So we get a coarse image every 5 minutes, and we can sort of filter through and get the cloud-free pixels and create a coarse map right away every day. But then we can also refine it as we get higher resolution satellite images for things like NOAA 20 VIIRS and NOAA 21 VIIRS, as well as Sentinel-2 and Landsat. And we bring those pixels in. We basically collect the best pixels and start formulating a map that we can get to the National Weather Service maybe 5 to 14 days earlier than they would normally get that information. So we're providing them with some important information about where the burn scar is, so that when they're doing their modeling of where the thunderstorms are going to happen, they can issue a flash flood warning or debris flow warning earlier, and save lives and property, which is the mission of NOAA and the National Weather Service.
So the work that I do overlaps with what we call fire danger assessment. So remote sensing can be used to look at what you have on the ground before the fire, to understand the possibility of fires and how they might be affecting the landscape. The USGS has a program called Wildfire that leverages Landsat primarily to map what you have for fuels. They do this now on an annual basis, so that the operational people can know what they have out there when the fire starts. The Wildfire products include things like the fuel type, the condition of the fuel, what the surrounding landscape's like, topography, things like that are really important for when people are trying to take care of incident. And then I've been funded over the years by NASA to look at how we can mature science-based knowledge into things that are valuable for practitioners. I use, for example, help develop some of the work using imaging radars. These are a radar on satellites that map the landscape, and what they're primarily sensitive to is the moisture conditions on the ground. So you can imagine that if you're able to see what you have for moisture conditions, you can understand fuel moisture and therefore understand the vulnerability of those fuels to fire. So developing how we can use imaging radars for fuel moisture and fire danger mapping at several scales is something that is being developed right now within NASA, so that we can have that kind of knowledge for our practitioners and improving their knowledge of what's happening long before the fire and then during the incident.
kind of lean off on what Nancy was saying. There's a couple key characteristics that impact, how bad a fire is going to be. The wind conditions, which unfortunately we don't generally have a lot of control over, moisture conditions, which we also don't have a lot of control over, and the amount of fuel or woody debris that's accumulated at a site, which we could theoretically have some control over and that we could burn it, right? So a lot of the work that I do relates to prescribed fires to eat up all or some of the fuel that's accumulated. So if there is a wildfire, it won't have as much fuel. So anyway, my work really relates to trying to figure out ways that we can use terrestrial laser scanning to document how effective a prescribed fire was. So we could scan a location with a terrestrial laser scanner before there's a prescribed fire, and then after the fire we can scan it again and then hopefully use the difference between those two measurements. So fire bosses and land managers want to be able to document like how well the prescribed fire that they implemented and that generally taxpayers paid for was in terms of actually reducing the fuel load or the amount of material at that location. And then another component is trying to predict how bad how the fire might spread, how quick it will spread, just the severity of the fire in general. And there's a set of different models that it can accomplish that, but they require certain inputs. So generally it's information about wind and moisture, topography, and then fuels. So an example is the quick fire model, so that people can get a more reasonable or more realistic explanation of or prediction of the spread of the fire over time.
And one of the things I think is really exciting about the work that Aaron and Nancy are doing with prescribed burns, and I know Nancy's involvement with FireSense, one of NASA's programs, is that they're documenting how fires behave and are able to monitor them. And in a prescribed burn situation, they can deploy resources and have them staged and ready to go, so they can really document and collect important information about the fire, whereas most of the fires I deal with are out of control wildfires that everyone's scrambling to try to catch up to and figure out. But the information we get from these models that Aaron referred to and knowing about the fuels and that Nancy referred to is we can try to at least estimate arrival time is one of the terms they use, is when is the fire going to get to a certain place based on the weather patterns and what we know about the fuels on the ground and all that information. So the better our databases are integrated and the better we understand the behavior of fires through the modeling and the prescribed burn research helps us respond better to the wildfires when they're actually happening and out of control.
So Sam, I want to come back to that for just a second. And you're talking about responding to these fires, and Nancy, I want maybe you guys can wrestle with this issue a little bit more. But talking about some of these recent fires like we've seen in California and some of these other fires that they happen, and the window is so small for response, right? Especially in these highly populated areas, or you're talking about arrival times and different things, but. Sam, how is this type of information being, one, how and when is it being created? But number two, how is that being relayed to folks on the ground to, essentially, you're seeing this stuff from a satellite, you're able to process it, you're able to create some really useful information, but then getting that out to the folks on the ground and actually implementing things that matter. How does that process work?
Yeah, it's a really good question. So what the larger kind of program I'm involved with is called the Next Generation Fire System, or NGFS, and its whole purpose is it's actually a repurposing of a volcano detection algorithm that is being applied to wildfires, and it's much more sensitive, and it includes lots of different sensors and inputs than the original volcano one. But what NGFS does is it has it takes every 5 minutes or even every 1 minute on the mesosector of some of the geostationary satellites, which is kind of a focused telescopic view of certain areas that's directional. But at any rate, every 5 minutes we get a CONUS, a whole continental United States view of thermal anomalies every 5 minutes, and that's just a snapshot that's continuously happening. And so we have these dashboards that essentially are alerts dashboard that are publicly available now on if you just search NGFS fire detection, you'll find it in Google. And these dashboards are actually, they're still experimental, but they're being used by the National Weather Service alongside their weather software AWIPS. And so it's sitting there on their desktop, and it refreshes every couple of seconds, and they're the first to know when there's some thermal anomaly. They have to decide whether it's something they care about or not, and they can filter based on various criteria that come with the detection, things like fire radiative power, or how many minutes this thing has been detected consecutively. Like, was it just a dumpster fire somewhere that went out fairly quickly, or is it something that's growing and getting stronger? That information is available at their fingertips now, and they can filter it based on their location. So they're not, somebody in Colorado isn't too worried about the fire in Aaron's backyard in West Virginia, but somebody in West Virginia might be really concerned about that fire. So they can filter this dashboard to only look at fires in West Virginia or in, other parts of the country. So it's a very powerful and somewhat universal tool that can be customized to the user. And so the National Weather Service is actively using it now, and they're the ones responsible for announcing the discovery of something new. There's a whole coordination effort with Forest Service and USGS and state emergency managers, and there's a whole network of fire people that through the NIFC, National Interagency Fire. I don't know what the rest of it is. Nancy probably knows, but at any rate, the fire coordination has come a long way in the last couple of years, even, and some of these programs are designed to leverage existing relationships, and there's a lot of training that's going on to bring, and it's cyclical too, because every incident we learn more about what information should be included and what are they missing, what do the people on the ground really need to know, and how can we simplify our information so that they don't have to paw through it, but it's just obvious. And actually, we just had some visitors from Alaska, and they have from GINA at Fairbanks. It's their Geospatial Institute. The fire issues are different in different regions, and one of the concerns they have in Alaska is permafrost, and so a fire can damage the permafrost just from its heat, and there's certain areas where they don't want that to happen, and so there's different criteria for whether a fire is important or not, based on what it's near and what threat it might pose to different resources or humans or whatever might be in the way or inadvertently affected by that fire. But I know Nancy's been involved with a lot of the kind of coordination efforts and the ways that different agencies are connected to each other and how they respond to and use the information. So maybe she can speak to some of that.
Yeah, it's the National Interagency Fire Center in Boise, Idaho, is where a lot of the kind of the nerve center of when wildland fires happen. They monitor for fires. As Sam was saying, the immediate stuff comes from the NOAA weather satellites, and that system he's talking about, and then that gets integrated into other things, like I mentioned, the land fire products that tell you what's in the place that's burning. NIFC is, as it says, interagency. So Department of Interior, the USGS is in there, the Park Service is in there, and the U.S. Forest Service and other land management agencies, Department of Indian Affairs. They all have little pieces of at NIFC, and they work closely together. They have a system called the IFTDIS, the Integrated Fire. Oh boy, I'm not going to get IFTDIS. The information system is the last two parts of IFTDIS, and that pulls in a lot of these mostly remote sensing derived information. When you're talking about geospatial information, it's going to be remote sensing derived. So that's kind of the nerve center of when you have fire operations. But they work all the time. They're year round, keeping an eye on all the different places that have fire. Remember that the fires in California that we all know as relatively notorious, they happened in the first week of January. So when we think about a fire season, it's not always just the summertime. It's all over the place within the United States. So the satellites that Sam's talking about that monitor are very important for that. And then the satellite Landsat is very important for understanding the context before and after. And then some of the work that I was mentioning, using imaging radars and other microwave systems for monitoring kind of the ephemeral conditions, those are up and coming. And what the idea here is we have an information platform where we can integrate these different types of spatial data sets and allow us to put them all together for both incident command work during the fire and also planning, logistics. They send firefighters all over the country and even all over the world, depending on what the conditions are for the fire danger conditions. And that is very much derived from what we learn from satellite remote sensing. And of course, on the ground, you have to have knowledge of that. But really, the satellites are what give us the big picture so that you can do that broad scale planning and then make your actions that are informed.
Yeah, I just have a question real quick for I know Aaron and Nancy have worked with fuels a lot, and I know an input that's of concern is fuel moisture, which gives you a sense of how readily those fuels might burn. And I'm wondering, is remote sensing used to monitor fuel moisture? Either Aaron or Nancy.
Well, and I'll let Aaron answer. He comes from a different point of view, so I'd be like to hear. Right now, the fuel moisture is developed with really weather indicators, and it's actually Smokey Bear at your. You might be driving down the highway and see that the fire danger is low or medium or high. So those signs with Smokey Bear there are based on weather metrics of what there is for conditions in that area, in that national forest. Those are all within national forests or national parks. So primarily they're driven by what is predicted or known with weather conditions. Fuel moisture has a lag effect, so they'll put in like antecedent weather conditions with that. Now, what I'm talking about with remote sensing, adding in the microwave sensing is new. There's a satellite called the Soil Moisture Active Passive SMAP products allow you to. NASA has a product that allows to measure soil moisture that goes into meteorological models, and it's also being integrated now to fire danger models. So we can, and fire danger is a word that we use that really is driven very much by the conditions of the fuels. And those are both long-term, you get your forest that comes and goes, but really very short-term when it comes to weather-driven fuel moisture and, as Aaron said, wind and such. I'll let Aaron add to that.
Yeah, I think it's fair to say that directly mapping fuel moisture is very difficult. Nancy's correct that This is a lot of times done more indirectly. I know for a lot of fire models, they'll parameterize it with certain fuel information and then maybe run a couple different scenarios at kind of a low end moisture to a higher end moisture to something maybe more, kind of characteristics so they could get a sense of what the variability might be. I know there have been people that have looked at LiDAR as a technique for trying to look at moisture both in the subcanopy and in the canopy. I mean, there is definitely a correlation between like near infrared reflectance and moisture content, but it's difficult to turn that into a real measure, like a physical measurement of moisture. And there's some correlation between moisture content and like radar backscatter also. But again, all of those are still it's kind of difficult, at least at a local scale, to get a really good moisture measurement. And another kind of key factor is that as the fire progresses, the moisture content will change. The fire itself is going to impact the wind conditions. If you have vegetation that's removed, that's going to create less wind drag. So it's a really complicated dynamic system that's kind of like with all these weird feedback loops. So that's something people are still working on, especially at the local scale fire spread modeling, because it is so complicated and we do have a lack of information on things like moisture.
That is super interesting.
So I'm gonna change the direction just a tiny bit, and then we'll come back to this. I know Brad has some other questions, but I'm gonna direct this to all three of you. But I want to start with Nancy because Nancy, you and I have had a chance to talk about fire and the work that you've done and projects that you've been involved in at different times, and some of the things that you are looking at, and we've talked about this idea of the impacts of fire sociologically and on communities, and this is not necessarily your area of expertise, but what I'm really interested in, having been, I live in the West, we have a lot of smoke, we have a lot of wildfires that pop up every single year, air quality goes down, and there's a big human impact to this. And I know that you're involved in a project right now that is looking at some of these impacts of smoke on communities, and I'm wondering if you could talk a little bit about that, because it is the visible part besides the fire and the property destruction. The smoke is something that impacts many more people, across large, vast areas. And maybe you could just talk a little about what's being done looking at that from your perspective.
I love to, because I'm an interdisciplinary scientist. As much as I'm an ecologist, I've learned so much from my atmospheric science friends when it comes to smoke. And now I'm learning quite a bit from social science collaborators on the project that you're talking about. And it's so very fascinating because as a physical scientist, I think, okay, we can measure this and model that and get an answer that has a number, and maybe it even has some kind of uncertainty around it. But what does that mean for people in the communities when it comes to smoke that's impacting their community? And I don't live in the West. I live in Michigan, where we get some of that smoke here and there, and the sky will be hazy. But in the West, there's some communities that oftentimes get smoke for many, many days. And sometimes they get little bits of smoke for all summer long, or they might have a summer that has very little smoke. So they get different conditions. Many people who live in some of these communities that are hit more often are kind of used to it. It's what you have. It's why we live where we are. The project that I'm funded by NASA's Interdisciplinary Science Program includes myself and my colleague Paige Fisher at the University of Michigan, who's a social scientist, and we're looking at the perception of risk to people from being exposed to smoke, and then how they respond to that risk. What are they doing to deal with the fact that they live in a place that has a lot of smoke, or maybe they've just had one time that it really was a problem for them? How can we gauge their perception of how bad that is for them, first of all, and then what they do to respond? For example, they could spend their days inside instead of outside, turning on air conditioning if they have it, or maybe even just visiting a friend and getting out of town for a day or two. What are they doing? That's what that part of the project is coming up. And stay tuned. And I'd say in a year and a half or two, we'll have some results from that work. I've just found it very fascinating because as a physical scientist, I always like the numbers. And as it turns out, the social scientists do too. They get this all down into very quantifiable ways of understanding people's behaviors. And it's a great project. I do want to say that the work that we're doing is in rural parts of the United States, the Western United States, and we're focusing on rural communities rather than urban communities because, and in some ways, it's because their lifestyle is very different. And what I just said about finding ways to respond to smoke. Sometimes quite a bit of people who live in rural areas are working outside as their standard, everyday life. They're farmers, they're people who just have an outdoor lifestyle because that's what they do. Whereas in urban settings and even suburban settings, we have a different way of living. We're inside more, we can turn on air conditioners and things like that. So the questions we're asking are focused on these communities where we want to make sure we're understanding how they're dealing with conditions that are getting worse. There's a part of my part of the project, which is the physical, smoke modeling. We're looking at long-term trends in the Western U.S., and we are definitely seeing more and more longer and higher concentrations of smoke across communities. So that research results will be coming out in a couple years, so you can learn about how really changes in land use and climate have really impacted the way fire is operating in the Western U.S.
My involvement with smoke has mostly been in visualization and mapping, so that we can take smoke forecast models that come to us in a kind of GRIB 2 three-dimensional arrays, and map that into something that works in a web map, and be able to animate it so we can see where the smoke we expect it to go. It's based on weather models, and you kind of inject the fire radiative power at a point and then see where the smoke plume goes. So, and then we can validate that with what's really measured. And so that's kind of my involvement. Another aspect of that is done some work with a group called Love My Air, that is a EPA funded program that uses air monitors at different elementary schools and gets the kids involved in keeping track of the air quality at those places. And then we have there's a web map for that. Started in Denver, and we have one in Milwaukee as well. That so if you just Google Love My Air, you can find it. And we add our visualization layers to those maps so the students can see what the air quality is looking like in terms of smoke, but also what we call aerosol optical depth, which is a product that's produced by some of the weather satellites to indicate air quality for aerosols.
Well, I see that the ref is getting ready to give us the 3 count here. So I was going to ask for any final thoughts about wildfire analysis. There's all these new kinds of technologies coming down the pipe. There's FireSat that's promising that even with the help of imagery and AI, it'll be able to detect fires as small as 5 meter by 5 meter on the ground, and all kinds of other things. But before we wrap up our match, I was going to ask each of you for some final thoughts on things. I was going to throw this first over to Sam.
Well, I think that it's a hard time in terms of being affected by fire right now in recent years, but it's a great time to be studying fire because there's so much material to look at. So that sort of sounds a little bit dark, but we are at a good we're in a place where technology is improving at a really dramatic rate, and our knowledge and ability to apply that technology to fire is giving us a better handle on what's happening, and some of the ways we can be more resilient in dealing with it as communities. And I really appreciate the inputs from Nancy and Aaron on that, because it's really kind of you're getting a full picture here of the from fuel to ash, and everything in between. So I appreciate this group conversation. So thank you.
I can see Nancy headed over to the top rope there. Nancy, what's your final thoughts here?
My final thoughts are that we're just starting to scratch the surface on how remote sensing, Earth observation, geospatial science can help with this problem set, because as much as I think building capability within artificial intelligence and machine learning is going to be very amazingly helpful, you can't do that without a lot of data, and you want data that is comprehensive and useful. Right now, when we are looking at fires from satellites, except with the exception of the GOES satellite, which operates at fairly coarse resolution, all of our ability to look at fires is with polar orbiting satellites, which mean that it passes over the site only once or twice a day. It's not seeing a place all the time. As I said, the geospatial satellites do that at a coarser resolution. So really the next step in what FireSat hopes to do is to have a constellation of satellites looking and being able to be what we call persistent in looking at places. FireSat, Wildfire Sat, which is the Canadian one, other ideas are all wonderful. Primarily they're looking at where is the fire, and maybe some information on the amount of energy. But really going forward, there's a great potential to use exactly that type of observational capability, but kind of beef it up some by looking at multispectral mid-IR to thermal, so that we can understand things like the level of burning. What type of burning do we have? What's the intensity? What different kinds of smoke are coming out because we have different burning conditions? So that's the future. I'm very excited about that. And as I said, as well as integrating the microwave, the radar knowledge, more consistency. Which, by the way, the NISAR satellite L-band radar went up just a month ago. And we will be having a lot of great ways to develop new capability for doing fuels monitoring and fire monitoring with synthetic aperture radar from the NISAR satellite. I have to mention that because that's what I've been working on for so many years. So thank you for giving me the opportunity to do that in my last few words.
Sounds good. And Aaron, go for the roll up in the pin.
One of the challenges we're facing is that a lot of our tools that we use for making predictions is empirical modeling or supervised learning. We're effectively using labeled data to train a model, like a regression model, to try to estimate something that you want to know. And that really does rely on having good labeled data. So a lot of the things we're interested in when it comes to forest fires, like fuel loadings and canopy bulk density and canopy heights and canopy base heights, things like this, they're actually not simple to measure. And so what we're generally doing is we're going out in the field collecting estimates of these things using things like field plots or transects, and then we're using those ground observations and trying to relate them to our spectral measurements, our LiDAR variables, or our radar variables to try to make maps across the entire landscape. But a lot of times those ground measurements are not super accurate, and they have their own flaws and biases. So in many ways, I think a lot of times we end up effectively creating a model that's just simply looking at the correlation between incomplete, biased ground measurements and spectral or LiDAR. So I think we've got to find ways to expand our toolbox a bit to do types of modeling and predictive tasks that don't rely so heavily on labeled data that in this case is just simply not there and not super reliable. So I'm interested in the application of things like digital twins, the generation of like synthetic forest stands as a means to kind of augment some of that. We're starting to see a lot of that kind of in the 3D GIS realm, and kind of pairing things like 3D models of trees or shrubs and trying to create these environments that you can kind of do like artificial experiments inside of. And I think it's those type of technologies that are going to get us past this lack of good quality field data that we need for modeling.
And that's the bell from the ref. But I wanted to thank all three of you, Sam, Nancy, Aaron. Thanks so much for venturing here into the squared circle today to grapple with all these issues surrounding wildfires and remote sensing.
Thank you, Brad.
Thank you.
Yeah, thanks. This was really fun.
And Chris, that's our wrap up for our match. But where can everybody find more about us online?
Thanks, Brad. And I, this was great to hear from everybody. And we could have gone for another hour talking about this and still barely scratch the surface. There's so much to wrap into all of this. But certainly for all of our guests, you can head on over to the Substack and see the show notes for this, and you'll be able to link to where you can find their bits and pieces of incredible information. For America View, again, Substack. If you haven't subscribed to the podcast, please do so. And then if you're interested in following along with other things, all of our social media accounts are at America View. Head over to YouTube. Some incredible videos and content created that's been created by the membership of America View posted there. And of course, americaview.org for a lot of data, downloads, all sorts of free resources. You can head on over to americaview.org and visit the website.
And as always, we'd like to thank our editor, Matt Wozniak, for making us sound good. And our theme music comes courtesy of Mr. Matthew Maxwell. Also, if you are listening to this podcast on a platform that allows you to leave a review, if you could do so, we would really appreciate that. Not only would it make us feel better, but it really genuinely helps get this show out into the hands of more people. But anyway, we'll be back soon with another episode. So until then, I'm Brad Shellito.
I'm Chris McGinty.
And you keep watching the skies for those spatial signals out there.